Welcome to this explainer. So, if you follow tech at all these days, you know we're just constantly bombarded with a spinning carousel of jargon. You know the buzzwords, right? They're dominating news apps, business magazines, your social media feeds. But honestly, even for those of us paying close attention, the exact boundaries between these concepts can feel like, well, an exclusive club with a language that's just constantly shifting. So today, we're going to fix that. We are mapping out exactly how all these pieces actually fit together. Which brings us to the exact question almost everyone has when they hear these terms thrown around interchangeably by CEOs, journalists, and developers. AI, machine learning, deep learning, are they just different names for the exact same thing? Or is there actually a real difference? Well, it turns out they are intimately related, but they definitely aren't synonyms. Instead of viewing them as completely, totally different concepts, I want you to think of them as a nested relationship between a goal and the methods used to achieve that goal. So think about transport. Transport is the ultimate goal, right? A car is one specific method to achieve that goal. And a sports car, well, that's just a much, much more powerful version of that exact same method. AI, machine learning, and deep learning work exactly the same way. All right, that brings us to section 1, the AI family tree, zooming in. Let's open up this kind of like a Russian matryoshka doll and define each level of this tech family tree, starting from the outside and working our way right into the center. Okay, so the outermost layer is artificial intelligence, or AI. This is the absolute broadest category. AI is simply the goal of making machines do things that require human-like intelligence. We're talking about reasoning, understanding, or making a decision. But what's absolutely crucial to understand here is that AI can actually include really simple rule-based programs that don't technically learn a single thing. To get this, you have to look at the contrast between the old way and the new way. Look at 1990s chess programs. Humans wrote every single rule. The machines simply followed those rules with literally zero learning involved. It was still AI, for sure, but it was incredibly rigid. Now compare that to modern machine learning, like your email spam filter. A spam filter is shown, say, 10,000 spam emails and 10,000 normal emails, and it just figures out the patterns all by itself. No human sat there writing rules about exactly which words mean spam. And that brings us to machine learning, or ML, a specific subset of AI. It's this crucial, game-changing shift from programming rigid rules to feeding a machine examples. Instead of a human hard-coding the instructions step by step, we feed the machine data, and we let it figure out the rules itself. Think about teaching a kid to recognize cats. You don't write out a mathematical formula or, rigid rules like pointy ears plus whiskers equals a cat. That'd be ridiculous. You just show them a few pictures or point at cats on the street, and their brain just figures it out. Machine learning works the exact same way. You show it the data, and it learns the patterns. Finally, we open the innermost nested doll to reveal deep learning. This is the sports car from our earlier analogy. Deep learning is a wildly powerful subset of machine learning that uses neural networks, which are actually inspired by the structure of the human brain. And what makes deep learning so special is its ability to handle massive, messy, unstructured data. Things like images, audio, video, text. This is the exact technology that powers complex, modern tools like facial recognition, voice assistants, and language models like ChatGPT. Now that we've mapped out the family tree, let's jump to section 2, how machine learning actually works. We're going to shift from definitions to the actual mechanics and peek under the hood to see how a machine actually learns. So machine learning generally breaks down into 3 main types. First step is supervised learning. This is where the machine learns from labeled data. That means you give it the input and the correct answer, like teaching that spam filter we talked about. Second is unsupervised learning. Here, no correct answers are given at all. The machine just looks at raw data and finds hidden patterns on its own, which businesses use for things like grouping customers based on buying habits. And third, reinforcement learning. This is learning by pure trial and error. The AI gets rewards for good actions and penalties for bad ones. That's the logic behind self-driving cars and game-playing AI like AlphaGo. Regardless of the specific type, creating a machine learning model basically follows a standard 4-step process. Step 1 is data collection. You gather examples to learn from. And remember this golden rule: garbage in, garbage out. The quality of your data literally dictates everything. Step 2 is training. This is where the model makes predictions, checks how wrong it was, and adjusts itself thousands of times. Step 3 is testing, where you test the model on data it has never seen before, just to prove it actually learned something. And finally, step 4 is deployment, where the model goes live out into the real world. But as you might guess, step 2 and 3 aren't always smooth sailing. There are two critical training problems we really have to watch out for. Think of a student preparing for a test. Overfitting is when a model learns the training data a little too well. It's like a student who memorizes the exact answers to a mock test, but when the real exam has a slightly different question, they completely draw a blank. Underfitting is the exact opposite. The model is way too simple. It's like a student who barely studied and fails both the practice test and the real exam. The goal is finding that sweet spot right in the middle, where the model learns the general underlying pattern.
So, what does the machine actually keep after all this intense training? It keeps what we call parameters. Parameters are the internal settings a model arrives at after training. Think of it like a massive music equalizer with thousands of sliders. Training is the process of adjusting all those sliders until the music sounds absolutely perfect. Those final slider positions, those are your parameters. They represent the actual technique the model perfected, completely separate from the raw practice data it used to get there. And to truly grasp the sheer mind-boggling scale of modern deep learning, just consider this number: 175 billion. A simple email spam filter might have around 10,000 parameters, 10,000 sliders on that equalizer. ChatGPT has roughly 175 billion parameters. That massive, unbelievable leap in parameters is what gives the model the incredible complexity it needs to write poetry, code software, and hold completely human-like conversations. Okay, so we have the sports car, but what about the fuel? Let's transition to Section 3, data science and the pipeline. This is the fuel that runs the engine, and the human pipelines required to refine it. There is this famous saying in the industry: raw data is like crude oil, useless until refined. I mean, we generate absolute mountains of data every single second, but a giant Excel spreadsheet of raw numbers doesn't actually tell a business what to do. Data science is the process of extracting meaningful, actionable insights from those giant messes of raw, unrefined information. Basically, data science sits precisely at the intersection of three pillars. First, statistics, to interpret the data. Second, computer science, to process all that data at a massive scale. And third, domain knowledge, which means actually understanding the specific business you're looking at. Take Netflix, for example. They use computer science to process your clicks, statistics to find patterns, and their domain knowledge of entertainment to predict exactly what movie you're going to want to watch this Friday night, often before you even know it yourself. To see how this actually works in the wild, let's walk through a real-world 6-stage pipeline using a food delivery app like Zomato. First, they collect raw data: orders, times, locations, the whole shebang. Second, they clean it. And actually, here's a pretty shocking fact. Data scientists spend 60 to 80% of their time just fixing errors and removing duplicates in this stage. It's totally unglamorous, but absolutely critical. Third, they explore the data, spotting patterns like huge order spikes on Sunday nights. Fourth, they build a model to predict delivery times. Fifth, they interpret the results into dashboards for management. And finally, stage 6, they decide. The insights are used to make real business decisions or predict your exact delivery time live on the app. Because this pipeline is just so incredibly vast, it takes a whole ecosystem of specialists to run it. Data analysts explore the data and create the visual reports. Data scientists are the ones actually building the statistical and machine learning models. Data engineers, they act kind of like the plumbers, building the heavy infrastructure and databases to store all that data safely. And finally, ML engineers take the models the scientists built and deploy them into live production so they work seamlessly right there on your phone. Wow, okay, we've covered a lot of ground today, unpacking the family tree of AI, peering under the hood of machine learning, and mapping out the pipelines of data science. But I want to leave you with one final thought to ponder. As you go about your day today, look at the apps on your phone. Every single time you order food, watch a show, or swipe on a video, which of your microscopic actions are being collected, cleaned, and fed into these massive, invisible pipelines right now? Thanks for joining me on this explainer, and keep questioning the technology around you.